Simply Civil integration. What is integration? Integrating a function is done to find the area underneath a function. And this is called the definite integration. And that's the reverse of something called differentiation. But hang on a minute, what are functions? Well, functions are essentially little number machines. So I've got a little number machine here. My number machine works when you have an input and put it into my number machine, turn it on, it whizzes and whirs, and out we get an output. Usually we write functions like this: f of x, the function, is equal to the square of x, and x will be our input. So in this case, if we input 2 into our number machine and the function is going to square whatever we input, it's going to do 2 times 2. And so our output, our y value, is going to be 4. Now you'll notice there you've got an x value and a y value, and that will be nicely plotted on a graph. And often in engineering we have functions, relationships between x and y values. They can be linear, straight lines, or they can be curved, which indicates they're nonlinear. Now expressing the area underneath a function and integrating it to find the area is a key skill in civil engineering. And we're going to do so, we perform the definite integral. Now for a straight line graph, let's say velocity versus time, you might want to find the area underneath it to find displacement, but that would be easy because it's a straight line, it's a linear function, and therefore the shape of the area underneath it is a triangle. And we all know to find the area of a triangle we would do 1/2 times the base times the height. But what about a curve, something which is not linear? Take our function y is equal to x squared, so everything we put into our number machine function is squared, and it would look a bit like this, a curve. The area underneath that curve is going to be some value, some number, multiplied by x times y, probably less than 1/2. Now, integration provides us with a really easy mathematical tool to do this for us, rather than us come up with whatever that number will be for every different curve that we might come across in our engineering journey. Integration, mathematically, focuses in on the curve of a function, and it does so. As it focuses in, it gets so close that that curve becomes a straight line. So if you had a magnifying glass or a microscope and you drew your function out on a piece of graph paper and you put it under the microscope and you zoomed in, you would know that eventually that curve would become a straight line, because the difference between the left-hand side and the right-hand side would be so small along the x-axis that there would be no change in height, the y-axis. This is what integration is doing. So we blow that little bit of the curve up so that we get a straight line. We can plot the straight line on the graph, and we would call that little bit of the curve, which is so small that it's become a straight line, we would call it dx. The d stands for what we would call an infinitesimally small amount of x. Infinitesimally is the same as infinitely. It just means it's very small. In fact, it's so small it doesn't actually exist, but that can be confusing. It exists mathematically. So what's the area underneath our infinitesimally small piece of x? Well, because it's a straight line though, it's going to be very easy for us to calculate that. It becomes a rectangle. So the area of that is going to be dx times dy. We call it dy as well because if you've got an infinitesimally small amount of x, you'll also have an infinitesimally small amount of y. So you see now, by reducing the curve to a straight line, it makes it somewhat easier for us to find the area underneath that little bit that we've reduced to a straight line. Integration is going to do that all the way along the curve and add it up. So dx means an infinitely small amount of x. That's a value of x which has effectively no width. Because it has no width, it doesn't change in y. This is called reducing the curve to the limit, which you might have come across. But if not, it doesn't matter. So for a function like the one we were talking about in our little number machine earlier, y is equal to x squared, the integration is going to reduce the curve to little straight lines all the way along the curve, find the area under each of those tiny little rectangles, and add it all up. And you'd write it like this. You'd say the area underneath the curve is the integral from 0, which is down here, this point, to the maximum value of x, which is here. That's the 0 to x of the function x squared for every little bit of x. So we split this line up into tiny little bits of x, those dx's. So that's how it would be written. Now often that elongated S shape is something that can fill a student with dread, but it doesn't need to. All that is the integral sign. The function is here. That's what we're going to integrate. So this is the integrand. The limits of the integral that you're performing is from here to here. In this case, it's 0 to x. And dx is the variable that we're going to integrate with respect to. Now, we use integration in fluids to calculate force. Now, for example, the hydrostatic force, and I'll have other videos on hydrostatic force, I'll try and link them here. The hydrostatic force of water on a submerged building. Here is a building, a structure, it's a simple cube shape, and let's say it becomes flooded with some water. It has a width which we can define with the letter B, and that's going to be in meters. And here is a body of water which is pressed against one side of the building. The height of that water is defined by the letter H, height in meters. Now, what we're going to do is we're going to integrate the pressure over this surface, multiply it by the area, and then add all of that up. And that's going to give us the force, which is the pressure times the area. So as we go along our surface of the building, we will start at the top and we'll go down a tiny little bit. We'll call that H1. And then we'll find out what the pressure is on this tiny little slice of building, horizontal slice, multiply it by the area, and then move on to the next bit just below it. Now the height of this is going to be a very small bit of H. So we're going to do the pressure on this all from the top all the way to the bottom, add it all together, and that will give us the force. So this is what that calculation looks like. You would write the force with the little subscript H. FH is here going to define the hydrostatic force, is equal to the integral from 0 to the top of the water, or the bottom of the water to the top of the building to the bottom of the water, the bottom of the building, from 0 to maximum value of water depth, of the density multiplied by gravitational acceleration, multiplied by the width of the building, multiplied by the height of the building, multiplied by our integrand, which is dH. Now, one of the other things is, well, how do you actually do that, maths? Well, the first thing you would do is you'd move the constants outside of the integral. So the constants here are the density and the gravity and the width, because it's a square shape. So we could put rho, g, and b on the left-hand side. And then we've got something that looks like that equation we had before, where we had x squared. And then we perform the integration. Now, again, that's another point at which students who haven't maybe done integration before will start to panic, perhaps. How do you perform an integration? What does that even mean? Well, a lot of integration and a lot of maths really is about learning rules. Maths is the grammar of physics. And those of you who are good at languages will know that if you understand the grammar of which a language is composed, it's much easier to learn a new language. So what am I saying there? I'm basically saying that maths is, for the most part, it's actually about learning rules. It's not so much about being technically gifted at maths. There is an element of that, of course, and it's something that I'm not particularly good at. But fundamentally, for the most part, when it comes to civil engineering and completing civil engineering courses, up to a certain point, it's more to do with whether you have learned those rules. So when it comes to integration, you can do a lot of it just by knowing what the rules are. Now, in this case, to perform an integration, what you might want to remember is that if you have a variable x, and here x is on its own, we could write x raised to the power of 1, but a value just on its own is effectively raised to the power of 1. To integrate x, you would add 1 to the power. So if it's x to the 1, it becomes x squared, and then you divide by the same power. So if it was x squared, it would become x3 over 3, and so on. Again, if you differentiate, it's the other way around. So in this case, we just need to recall that the integral rules show that x raised to the power of 1 is equal to x squared over 2. And we replace x with h. We can say, well, we've got h to the power of 1, so I'm going to do h squared over 2, and that's my integration. And so my equation, once I perform the integration, and if you perform the integration, you can get rid of that fancy, elongated, elaborate s of the integration sign, and you can write the horizontal force is equal to rho, the density, times gravity, times width of the structure, multiplied by the height of water squared over 2. Now, more often than not, you will see it written in textbooks like this. This is the hydrostatic force equation, 1/2 rho g h squared times b, or b times h squared. And that's the pressure times the area. And that is the result of integrating the force across the whole of the submerged surface. And that is, I hope, simply civil integration.